Hi everyone, welcome back to Chem Help ASAP. In this problem set video, we are going to be working with acids and bases. So first we will do problems where we identify acids and bases, then we will do some simple problems with the pH and the Poh scale, and then we'll start to do some calculations. So we will calculate pH, Poh, hydroxide, and hydronium concentrations. Next, we'll talk about the difference between strong and weak acids and bases, and then we will finish out with some titration problems. Let's get started. Here is our first exercise. We are going to identify acids and bases, and then we are going to write net ionic equations for each of them. However, if we find that a compound is neither an acid or a base, we are going to specify that it is neither. Our first compound is potassium nitrate. If it is an acid, it will have a proton to donate. Well, potassium nitrate doesn't even have any hydrogen, so it cannot be an acid. If it is a base, it will have hydroxide ions. Again, we have no hydroxide anions, we have the nitrate anion. So this is neither an acid nor a base. But because it is a salt, we can still write a net ionic equation for it. Here is our net ionic equation. Let's take a look at our next compound, magnesium hydroxide. We are looking for either protons to donate or hydroxide anions. The name itself gives it away, magnesium hydroxide. It has hydroxide, therefore it is a base. The net ionic equation for this base is right here. Our next compound is sulfur dioxide. We have no protons to donate, we have no hydroxide. Sulfur dioxide is a covalent compound, so it is neither an acid nor a base. And because it is covalent and not ionic, there is no net ionic equation. Though that one was easy. Let's look at our last compound, HBr. No hydroxide, but yes, there is a proton we can donate. So this is an acid. The name of this compound actually is hydrobromic acid. The net ionic equation is right here. Let's do one more identify question. Here is ethane. Is it an acid, a base, or neither? We do have plenty of hydrogens. There are no oxygens, so definitely no hydroxide. The question is, are these hydrogens acidic? Can they be donated? The answer is no, because this is not an ionic compound. This is a covalent compound. So ethane is neither an acid nor a base. Now let's work a little bit with the pH and the Poh scale. So our question reads, you have a solution at a pH of 8. You need to make it neutral. By what factor do you need to change the pH? Do you need to increase or decrease the concentration of protons? Let's put our pH scale up. Here we go. Our scale will make it easier to answer this question. We are starting at a pH of 8. At a pH of 8, our concentration of hydronium ions is 10 to the negative 8. We need to go to a neutral pH. Well, what is the pH of a neutral solution? The pH of a neutral solution is 7. Here is our neutral pH on our scale. So we need to make the step from a pH of 8 to a pH of 7. We are going from a concentration of 10 to the negative 8 to 10 to the negative 7th. That is an increase in concentration, and specifically it is an increase in concentration by a factor of 10. Let's do a question with the Poh scale. What is the concentration of hydroxide ions if the Poh is 2? What will the value of the Poh be if you decrease the concentration of hydroxide ions by a factor of 1,000? Let's first find the concentration of hydroxide ions at Poh of 2. Here it is on our scale right here. So at a Poh of 2, our concentration is 10 to the negative 2nd. Now if we decrease this concentration by a factor of 1,000, that means we are going to take 10 to the negative 2nd and divide by 1,000. That is going to take us to 1, 2, 3, 10 to the negative 5th. You could also call that 3 orders of magnitude. So our new concentration of hydroxide ions is 10 to the negative fifth, which corresponds to a pOH of 5. What these problems hopefully clarify is each time you change the pH or pOH by 1 unit, you're really changing by a factor of 10. Now let's use our mathematical equations and do a little bit of math. We need to fill in our table here. You might be looking at this table and wondering how we're going to fill in all these blank spaces. But let's take a deep breath and just take this step by step. We will start with our first row. Since we have our hydroxide concentration, I am first going to calculate the pOH. So here is my equation for calculating pOH. I am going to plug in my hydroxide concentration like so. Put this into my calculator and I get a pOH of 11.35. Now that I have my pOH, I'm going to calculate my pH. Here is my equation for pH and pOH. Again, plugging in my value for pOH, I get a pH of 2.65. One more value in this row, we need to calculate the concentration of H+, or if you prefer, hydronium ions. I am going to use this equation right here. Plugging in my hydroxide concentration, I get a hydronium concentration of 2.23 times 10 to the negative third. Now I have all 4 of my values. My last question that I want to answer is this an acid or a base? And because the pH is less than 7, this is an acid. That's the first row done. Let's go on to the second row. This time I'm starting with my hydronium concentration or my H+ concentration. So let's calculate pH. Here is my equation. I plug in my hydronium concentration and I get a pH of 7.24. Now that I have my pH, I'm going to go ahead and calculate my pOH. Here is my equation. Plugging in my value for pH, I get a pOH of 6.76. Finally, I need my concentration of hydroxide. Here is my equation. Plugging in my value for pOH, I get a hydroxide concentration of 1.74 times 10 to the negative 7. Now I have all my values. Let's determine if this is an acid or a base. In this case, let's look at pOH. Because pOH is less than 7, this is a base. Now on to my third row. I am starting with my value of pOH, so let's calculate the value of pH. Here is my equation. Plugging in my value of pOH, I get a pH of 4.07. Now that I have pH, I'm going to calculate my hydronium concentration. Here is my equation. Plugging in my pH, I get a hydronium concentration of 8.51 times 10 to the negative fifth. The last value I need is hydroxide. I will use this equation right here. Plugging in my value for hydronium, I get a hydroxide concentration of 1.17 times 10 to the negative 10th. Now to determine if it's an acid or a base, I'll switch back. Let's look at the pH. Now because the pH is less than 7, this is an acid. On to my final row. Now I am starting with pH. So let's calculate pOH. Here is my equation. Plugging in my value for pH, I get a pOH of 0.6. Next, let's calculate the concentration of hydronium ion. Here is my equation. Plugging in my value for pH, and I get a hydronium concentration of 3.98 times 10 to the negative 14th. The last value I need is my hydroxide concentration. Let's use the pOH for that. Here is my equation. Plugging in my value for pOH, and I get a hydroxide concentration of 0.25 molar. Now to determine if it's an acid or a base, let's go ahead and look at our pOH. Because our pOH is less than 7, this is a base. When determining these values, you may use any of the 4 equations that you would like. You can also do it in any order that you would like. So you may find yourself doing these calculations a little bit differently than I did them. That is perfectly fine. We will end up in the same place. Also determining acid or base, you can look at pH or POH. You can even look at hydronium or hydroxide concentration. It just matters which way makes the most sense to you. Now let's calculate values for actual solutions of acids and bases. Our first problem reads, calculate the POH of a solution when 11.2 grams of hydrobromic acid is dissolved in 2.75 liters of solution. And they give us the net ionic equation right here. The thing that might throw you in this question is hydrobromic acid is obviously an acid, but they are asking for POH, which you will associate with the base. However, every solution has a pH and a POH, as we will see. The first thing that I want to do is I want to calculate the concentration in molarity of my hydronium ion. To do that, I need moles of my hydronium ion. So starting with my 11.2 grams of hydrobromic acid, first I'm just going to convert that to moles. Here's the molar mass. Notice my grams cancel. My net ionic equation gives me the mole ratio between hydrobromic acid and hydronium. It's just a 1-to-1 ratio. Here is my mole ratio. My moles of hydrobromic acid cancel. I'm left with moles of hydronium. So my moles of hydronium are 0.138. Now let's calculate concentration. Here is my equation for molarity. My moles of solute have already been calculated. That is my 0.138. My liters of solution is actually given to me in my problem. It's 2.75. Plugging these values in, I get a molarity of 0.0503. Now I have my concentration of hydronium ion. So I can calculate my pH. Here is my equation for pH. Plugging in my concentration, I get a pH of 1.3. This makes sense. I have an acid in solution. I should have a pH of less than 7. However, the problem asked me for POH, not pH, so I need to simply convert pH into POH. Here is my equation. Plugging in my value for pH, I get a POH of 12.7. These problems can have a lot of steps, and while each step is not that difficult mathematically, putting them together in the right order can be a little tricky, so let's do another one. My next problem reads, how many grams of lithium hydroxide are needed to make a 500 milliliter solution that has a pH of 10.5? The net ionic equation for lithium hydroxide is given right here. Lithium hydroxide is a base. You can see it's giving us hydroxide ions in solution. However, the problem gave us pH. So let's first convert our pH to POH. So here's our equation. Plugging in my value for pH, I get a POH of 3.5. This makes sense. This is a base. I should have a POH of less than 7. How can I use that POH to help me find my grams of lithium hydroxide? Well, I can connect POH to concentration of hydroxide. If I can get concentration of hydroxide, I can convert back to lithium hydroxide. Here is my equation to get back to concentration of hydroxide. Plugging in my value for POH, I get a hydroxide concentration of 3.16 times 10 to the negative fourth. I have concentration of hydroxide, but how many moles of hydroxide do I have? To determine moles of hydroxide, we are going to use our equation for molarity again. Here it is. In this case, we know our concentration, we know our molarity right here. Our problem gave us our liters of solution. We have 500 milliliters or 0.5 liters of solution. We can calculate moles of hydroxide. So our moles of hydroxide are 1.58 times 10 to the negative fourth. Now that I know moles of hydroxide, again, I can use my mole ratio to get back to moles and then grams of lithium hydroxide. Starting with my moles of hydroxide. Here is my mole ratio to convert to lithium hydroxide. Again, notice that we're careful to make sure our moles of hydroxide cancel. Next, we need to convert moles of lithium hydroxide into grams of lithium hydroxide. Here is my molar mass for that conversion. Again, making sure that our moles of lithium hydroxide cancel. And my final answer is 3.79 times 10 to the negative third grams of lithium hydroxide. Looking at these two problems side by side, you can see the steps are actually very similar. They're just reversed because I was given different information in these two different situations. The best way to get more comfortable with these types of problems is, of course, to practice, practice, practice. Let's take a little break from math and let's talk about the concept of strong and weak acids and bases. First, we are going to write the chemical equation for strontium hydroxide and nitric acid. Strontium hydroxide is a base, it has hydroxide, and nitric acid, well, the name kind of gives it away, but you can see this proton right here can be donated. Now, to write these chemical equations, we need to know if we have strong or weak acids and bases, because that will determine what kind of arrow we use in our chemical equation. A strong acid or base will have an arrow to the right only. A weak acid or base will have equilibrium arrows, or arrows that point both forward and back. Let's take a look at strontium hydroxide first. Strontium hydroxide is one of our common strong bases. Because it is a strong base, we will use a right-hand arrow only. It will produce the strontium cation and the hydroxide anion. Notice that we do balance this equation. Next, let's look at nitric acid. Nitric acid is also a common strong acid, so we will use a right-hand arrow only. When writing chemical equations for acid, I personally find it easier to put water in as a reactant, although you do not have to. Using the right-hand arrow only, I will produce hydronium ion and my nitrate anion. Again, notice the equation is balanced. Let's do the reverse. So determine if the following are strong or weak acids and bases. So part A gives us carbonic acid, and here is the equation. The thing we really want to focus on here is we have a double arrow or an equilibrium arrow. This means we have a weak acid. Let's take a look at part B. We are given the equation for sulfurous acid. Again, we see the double arrow, the equilibrium arrow. This is a sign that we have a weak acid. So sulfurous is a weak acid. Finally, we have the equation for barium hydroxide. Focusing in on the arrow, we only have the right-hand arrow. So barium hydroxide is a strong base. Notice in all these problems, nothing was said about concentration. We may have a concentrated solution of these acids and bases or a dilute solution of these acids and bases, and it does not change if we have a strong or weak acid or base. It is all determined by if these compounds fully ionize or not. The way we know if it fully ionizes is if we have a right-hand arrow only. Of course, what is one of the most common things we do with acids and bases? We react them or titrate them. So let's work on some titration problems. A student needs to know the concentration of a solution of sodium hydroxide with high precision. She makes up 3 samples of a known amount of perchloric acid. She titrates each sample with her unknown sodium hydroxide. This is the great thing about titration, is you can get concentrations to a very high precision. So we have her data table here. We have 3 samples, 1, 2, 3. We have each mass of perchloric acid. And we also have the volume of sodium hydroxide needed to fully titrate each sample. So here are our questions. What is the concentration of our sodium hydroxide for each sample? What is the average concentration? Do you think there is much error in her concentration? And they give us the molar mass of perchloric acid here, that's nice, and the molar mass of sodium hydroxide. Before we do any math, what is the reaction of perchloric acid with sodium hydroxide? We are reacting an acid with a base. So I know one of my products will be water. My other product will be a salt right here. You can see my cation comes from my base and my anion comes from my acid. Check and make sure that this is a balanced chemical equation. Yes, it is balanced, and it's always nice to see 1-to-1 mole ratios. Now we are ready to jump into our math. Taking our information from sample number 1, we have 0.2862 grams of perchloric acid. We are doing a reaction here. We know we are going to do stoichiometry. So let's first convert that into moles. Here is the molar mass given by my problem, making sure that my grams cancel. So we have 0.00285 moles of perchloric acid. Perchloric acid and sodium hydroxide react in a 1-to-1 ratio. So to neutralize all these moles of perchloric acid, we need to do a little bit of stoichiometry. So here again are my moles for perchloric acid. Here is my mole ratio between perchloric acid and sodium hydroxide, making sure that my moles of perchloric acid cancel. This is why it's wonderful to have a 1-to-1 ratio, because of course our number of moles is exactly the same as our moles of perchloric acid. So we know how many moles of sodium hydroxide we needed to neutralize this sample of perchloric acid. But what we're really after is the concentration. So let's get the equation for concentration up. Here is my equation for concentration. I need moles of solute and liters of solution. I just calculated my moles of solute. Can I figure out my liters of solution? Well, that is actually given to me in my data table. Now that is milliliters. We do need to convert to liters, but that's an easy conversion. Let's put our numbers in. Here are my moles of sodium hydroxide, my liters of solution. My concentration is 0.1 molar. We follow the exact same steps for sample 2 and sample 3. I will not bore you with rewriting all these equations again, just with slightly different numbers. Here is a table summarizing each of our concentrations. You can see here's 1, 2, and 3. We have done the first part of this question. We answered what is the concentration of sodium hydroxide for each sample. Now let's calculate the average concentration. Of course, this is fairly easy. Here is our average concentration. Now let's think about the error in her concentration. Are her concentrations fairly close together? Yes, they are actually very close together. Look, it's only in the 3rd decimal place that we have any variability. I think this student can be fairly confident that her average concentration is accurate. Let's do one more titration problem. A 40 milliliter sample of vinegar is titrated with a 1.01 molar solution of potassium hydroxide. It requires 33.26 milliliters of potassium hydroxide to fully titrate the sample. What is the concentration of the vinegar? The balanced chemical reaction is shown below. It's always nice when they give us the balanced chemical equation. You can see I have an acid reacting with a base. This gives me water and a salt. Again, my salt comes from my cation of my base and my anion of my acid. Since we do not know the concentration of the vinegar, let's start with the base where we do know the concentration. Here is my equation for concentration. I know the molarity. Do I possibly know the moles of solute or the liters of solution? I do not see moles of solute or grams of solute. However, I do know the volume of potassium hydroxide. This is my liters of solution. Let's plug those numbers in. Here you go. You can see I converted into liters. So I now know my moles of potassium hydroxide. We're still trying to get to our vinegar. But because we have our balanced chemical equation, if we know our potassium hydroxide, we can use stoichiometry to get to our vinegar. Starting with my moles of potassium hydroxide, here is my mole ratio between potassium hydroxide and vinegar, and making sure that my potassium hydroxide cancels. And now here are my moles of vinegar. Again, it's wonderful to have this 1-to-1 ratio. It makes the math so easy. Going back to my equation for molarity, let's just rewrite it. This time, I know my moles of vinegar. Do I know my liters of solution for vinegar? Well, going back to the problem, I see that I had a 40 milliliter sample of vinegar. So yes, I do know my liters of solution. Plugging in my moles of vinegar, my volume of vinegar, my molarity or my concentration of vinegar is 0.840. One of the tricky things in this problem is making sure that your volume of 40 stays with your vinegar and your volume of 33.26 stays with your potassium hydroxide. It's very easy to get those two volumes flip-flopped. I didn't do it in this problem, but it can be helpful to use a data table and list out everything you know. Acid and base problems are no joke, so I hope you found it helpful to work some of these problems with me, and thanks so much for watching.